In the fifth section, we will study the balanced field length, which is also the distance for the aircraft to stop under one engine operative or lose thrust. So now let's first introduce the concept of balanced field length, and let's move our eyes to the lower right hand side. And we have a graph. There are two curves. The horizontal axis is the velocity of the aircraft, and the vertical axis is the distance. So curve 1 is indicates the distance to fully stop, to bring the aircraft to fully stop. And curve 2 is the distance to reach a liftoff velocity. We can see curve 1 and curve 2 will intersect at a point, and that point, the velocity is called decision velocity. So for the decision velocity, the corresponding distance is so-called balanced field length. At the decision velocity, which means the distance to bring the aircraft to fully stop, or the aircraft for the distance for the aircraft to reach the liftoff speed are the same. So that's called balanced field length. So if the aircraft has a speed less than v1, the distance to reach a liftoff speed is larger than the distance to bring the aircraft to fully stop. If the aircraft has a velocity larger than v1, so it takes longer distance to brake the aircraft. And then we should make such a conclusion. Under one engine inoperative, if the velocity is less than the decision speed, the aircraft takeoff procedure should be aborted. And for the same OEI condition, one engine inoperative if the velocity is larger than v1, so the takeoff should be continued. The certification rules specify that the airfield length should be the greater of the following distances. The distance first is the distance required to accelerate the aircraft to decision speed v1 and then to take off at safety speed with one engine inoperative, or the distance required to accelerate the aircraft to decision speed v1 and then to bring it safely to rest. And third is 115% of the distance required to accelerate the aircraft to take off safety speed with all engine operating. So we need to check which is greater. The decision speeds are normally decreased when wet runways to take into account the reduced braking effectiveness. Otherwise, increased field length should be required. Concessions on screen height are made as a result of the reduced decision speed. So these are some extra considerations. Showing here some typical aircraft field lengths. For example, the Boeing 747-400 has the longest field length, which is 3,322 meters. And for smaller aircraft like Airbus A300, it's slightly smaller. So now let's see how do we calculate the field length. And an approximate method for calculating the balanced field length is similar to that for the takeoff ground run, which is we have done earlier. But to calculate the balanced field length, we should have some specific condition that thrust is 0 because we want to bring the aircraft to stop, so we need to shut off the engine. And the lift is possible at 0 if spoilers are deployed, because we want to have increase the drag. And the parasitic drag should take into account the effect from the spoilers, because once the spoilers are applied, the drag is larger. Okay, so now let's see the governing equation. Again, from the second law, m times acceleration equals minus d minus f, because the thrust is 0, so we just didn't list the thrust in the right-hand side. And you may notice now we assume there's no runway slope, the gamma r is 0 then. And we know F equals mu times W minus L, so we just plug in F. So we have the acceleration relates the right-hand side. As before, considering a given time frame delta t, the aircraft's speed changes by delta v, and it covers a distance delta s equals v times delta t, and that's in the calculation of ground run distance. We have acceleration equals v times dv divided by ds, and since v dot is acceleration, we can combine those two equations. We have the governing equation shown below. Just now we have the ds and the dv relation, and then we can have a rough approximation for the stopping distance. And by doing this integration, we assume lift and drag is independent from velocity. So this is really a rough approximation. We assume d and l is independent from v. Okay, but in reality, L and D changes with velocity. So we need to revisit the equation here and plug in L and D. L is half rho a squared times CL, right? And D is half rho a squared times CD. Then we do some manipulation, put CL and CD together in a bracket, and then we make ds explicit, so we have a proper differential form. Then we want to do the integration. Okay, so this is what we get from the previous slide, and we can see the s changes with velocity. Okay, so if we want to get the stop distance, we need to do the integration. And the velocity is integrated from v1 to 0, because v1 is a decision speed, 0 is a stopping speed that bring the aircraft into fully stop. Okay, and actually the integration procedure is the same as we do for the ground run distance. So I'm just not doing the integration here, and it gives you such a relation. Okay, so that's a stop distance. Then the total balance field length is S1 plus S stop. S1 is a distance for the aircraft to reach V1, the decision speed. And this is a similar curve as we've seen at the beginning of this section. And again, we have two curves, and we can see the decision speed and the field length. And this is kind of graphical method to determine the balance field length. So on the one engine inoperative, we can test the aircraft at different speeds to accelerate to fully stop. That's the upward going curve. And the downgoing curve is the distance aircraft to reach the liftoff speed. And so these two curves intersect with each other. We can get the decision speed and also the balanced field length.